Alright, welcome back to another video. So, I can usually do about an hour. We're moving on to a problem resolution. We will try first with a naive approach, as we did for time-based anomaly detection. We can use the z-score technique described to identify what is the acceptable range of values for this metric and use this to detect outliers. As always, this is all subject to interpretation. No algorithm will always be confident that the outlier detected is genuinely an outlier or that there is a good reason for this value to exist. A human interpretation is always needed before an action is taken. The following is the simple routine that will help us detect outliers in the Target metric. So obviously you meant to say target. There's a missing T. I don't know what happened to the T. It's got to be somewhere. It's probably cold and hungry in the streets somewhere. But there's really nothing I can do, especially since I'm not the author. Okay, so we were running the code examples. So it looks like we've got another few, one or two or however many cells to run. So let's advance the bookmark and then get that Jupyter. So the Jupyter server is still running. So let's see if we can open up the port. There we go. So we open up the local host to the port, and now we've got it running. We're on use case 2, and we're using one of these notebooks. The thing is, there's two of them, and I'm not sure which one we're meant to use. Both of them are for outlier detection, but one is for multivariate, and the other one is just for regular outlier, and the book didn't make it clear which one we were meant to use. I'm using multivariate because it says that there's new libraries to install, and the other one says that there's extra libraries to install. So we're starting new, so I'm going to use the new libraries, and then later we can use the extra ones. Okay, so I was running this, and I think I got down to a specific. Yeah, so I think I'll not clear and run again because this is where we left off. So I'll just run the next lines of code. So it'll end with the return outliers. Okay, so unfortunately I don't see that in this. So maybe I did need to use the other one. So let's look at the other one. That's not multivariate. Yeah, so we were using the wrong notebook. That's fine. We'll just switch to using the right one. Now we will need to prep the right one to run properly. We learned from ChatGPT. This exclamation point just means to install it. It doesn't mean to bring it into the notebook. So like it means to install it in the bash. So if you install that and then restart your terminal, or even if you're not in a Jupyter notebook, that might work. But when you're in a Jupyter notebook, you have to use the %sign because it's a magic method that installs it in the actual kernel that you're using the notebook in. And if you do it any other way, you're not going to have that available even though you installed it. Okay, so here's the next thing we have to change. We're not using it in Google Colab against the author's best wishes because I have a pretty nice GPU, so I figure I'll just put it to use. And yeah, I just don't want to do it that way, even though it's probably a better way. Okay, and then the other thing is, since we're doing it locally and not on not that other way, we need to change some of these import statements. So we need to change this to import it from the local files. All right. And I think that's it. So I'm gonna hit a Control S. I'm gonna go to the kernel and do restart and clear all output. All right, and now hopefully everything will run properly. So we'll get a warning here for the TensorFlow, but the warning just says that you can reconfigure it with if you reinstall it in a way that is probably better optimized. And then we also got another warning saying it cannot find TensorRT. I don't know what TensorRT is. I don't think it's relevant to this project. Okay, so we should see a lot of the same graphs that we saw before, but we've got this new section here for z-score outlier-based detection. So yeah, there's the graph that showed up here. Yeah, so that looks a lot better now. Before it kind of wasn't lining up. So yeah, because I was using the wrong notebook. So we have to get all the way down here to outliers, which is just the very next cell. And then I think we actually print. Yeah, we print them on the next page. So as in time-based anomaly detection, we are using the median, not the average, because it is more resilient to outliers. However, we are using the standard deviation, which is not that resilient. So our calculation could still be misled by those outliers. The alternative is to use percentiles. When we run our routine, we obtain the following. So we're going to get this output here. And there we go. So we got an outlier list. We've got two devices are outliers because of their memory utilization. And it looks very similar to what we see here. It looks exactly the same to what we see here. Well, no, not exactly, because the utilization is different. We're using our own numbers, generating our own values using that simulator that the author included. So the simulation came up with slightly different values. The algorithm has programmatically detected that there are two outliers and which those outliers are. If we had an automated system, we could be alerted of this condition without having to watch any dashboard for this. Let's try a more advanced algorithm, local outlier factor, LOF. We have mentioned this algorithm in the theory section of the book for anomaly detection techniques. This algorithm computes densities of data points and estimates the density around one data point in comparison with the densities on its k nearest data points. The computed local outlier factor is the ratio of those densities. If a data point is close to others, its local density is going to be very similar to its neighbors, which will result in an LOF, which we remember stands for local outlier factor, very close to 1. If a data point is very separated, its local density is going to be much lower than its neighbors, so the local outlier factor, or LOF, will result in a higher number, since the local density is in the denominator. Let's use it in practice. Okay, so we've got another cell to run. We need to do a bit of reshaping of our table to train the model. So we got to reshape our table here. All right, table is reshaped, and I think there's the LOF. Okay, yeah, table is reshaped. We will be using the LOF, local outlier factor, class from the PYOD library. It is actually an augmented wrapper on top of the more common local outlier factor class from scikit-learn library. Feel free to try that one or any other option. The contamination parameter helps setting the threshold to determine if a data point is or is not an outlier. It sets an expectation of what is the expected percentage of outliers in your data. You may need to try with different values if there is no historic view on what could be a normal value. So LOF equals LOF contamination equals 0.05. There we go. That's the cell here. We can then train the model with our data set and evaluate the detected outliers. Okay, so let's do that. So we're going to print out the training data, and then we're going to print out the threshold for a defined contamination rate. Okay, so the threshold is 1. And that's the same as there. The results show that out of the 200 observations, 2 of them are highlighted as outliers. We can review the returned LOF values, local outlier factor values, and we can see how the vast majority are 1, with the exception of 2 of them, which have a very high value and are clearly outliers. So there we go, y_test_scores. Perfect. Yep, everything looks good. And then, yeah, so we've got the 2 outliers here at the end. So we can see that it returned the LOF values. The majority are 1, but we've got the 2 at the end that are quite a bit bigger than 1. They're about 4 times bigger than the number 1. We can visually represent the histogram of LOF scores and get a similar perspective. So there we go. Get a similar, so we see how everything like there, and then close to 4, we see our 2 outliers there. So if I run it here, yep, same thing. Here's the 2 outliers, close to 4, but everything else, nearly all 200, are, oh, that's interesting, 0.0. I thought they were a value of 1. Okay, well, 0.0. But that's not what it said before, right? I thought it said, yeah, it's saying 1.0. So why is it not here? Let's, this is what ChatGPT is designed for. So let's get some education from ChatGPT. So what we're gonna do is just paste this whole thing in it. It doesn't even have to be in focus. Apparently, ChatGPT can do that. And let's get some extra information in there. So let's feed it this top part so that it knows that it's in a Jupyter notebook. It doesn't have to make guesses about what it's seeing. All right, and then let's paste in another screenshot. This time of the book. So let's see here where. And I'm kind of losing my place. So before we do that, let's advance the bookmark. So here's the current bookmark. It needs to be advanced. There we go. So we can visually represent the histogram of LOF scores and get a similar perspective. And this is where the bookmark needs to be advanced. And similarly, we can get to the actual outliers programmatically based on the predicted results by the model. So let's get that. And there we go. So far, the use case was simple, and the outliers were very easily identifiable. So let's complicate things a bit, because usually that's how life works. I can confirm that. The behavior of a system will usually be characterized by more than one data point. If we only focus on one, we may be missing perspectives that would be important to understand if it is an outlier or not. Therefore, while so far we have considered this problem to be univariate, so a single, now we will generalize it to multivariate. So there we go. Now it's confirmed. The multivariate notebook will be used next. We want to find out from our SD-WAN edge devices which ones are outliers, but not looking at a single variable, but looking at many, but not individually each. That would be a multi-univariate problem, but truly analyzing them as a whole. And I'll advance the bookmark. And now I do want to have this discussion with ChatGPT. So I'm going to say, why is the leftmost bar in the histogram at uh, near 0.0 and not near 1.0.
The leftmost bar in the histogram is near 0.0, not near 1.0, because it represents the lowest values in the dataset.
Okay.
Histograms display the distribution of data by grouping data points into bins along the x-axis and
But
counting
the
the number of
data
points that fall in
set,
each bin. From the context provided in the image, it appears that you are working with some kinds of evaluation scores or probabilities that range between 0 and 1. The histogram is showing a significant count of data points near the value of 0, indicating that many of your data points are close to 0.
did it though?
The exact nature of these scores, whether they're error rates, probabilities, or some other metric, will determine why they're clustered near 0.
But
Given
isn't the
significant
data
left skew of
set?
your histogram, it suggests that the scores
Wait, but isn't the data set showing that the values are close to 1 instead of 0?
Upon closer inspection of the data presented in your Jupyter notebook, it seems like I misunderstood the context. Let's reassess the situation. Data inspection. From the display table, y_test_scores, it appears that the values are indeed very close to 1.0.
Yeah.
For example, the values listed are all around 0.999999999999999, which indicates they are very high. Histogram interpretation. Given that the data values are close to 1.0, the leftmost bar in the histogram should correspond to these high values.
Right.
The confusion
should
might
be
arise
here.
from how the histogram bins are defined and what the histogram is actually plotting. Here are two possibilities. Bin range. If the histogram bins are not set properly, all the values close to 1.0 might be grouped into a single bin that appears at the beginning of the histogram.
Oh, it's a
This can make it
bin.
look like the values are near 0 when in reality, it's a matter of bin configuration.
Oh.
Plot scale. Ensure that the x-axis of the histogram is scaled correctly to reflect the range of your data accurately.
Then why are the other ones right?
To diagnose this,
Okay, so maybe it has something to do with the bin. I will feed you. Well, actually, no, you can see it. So you can see the Jupyter Notebook, and you can see histplot, and you can see plt.legend outlier score distribution. So like in that cell, that's where I'm setting the bins. So I guess maybe that might affect it some way. I'm not sure how. But the thing is, like in the graph, the MATPLOTLIB that shows up, the other values, the outlier values, are where you would expect them to be. They're right around 4, but it's the other values where I'm really confused why they're so close to 0 and so far away from 1 when the data shows that they're all at 1. Oh, but then I see something else. I see prior, and I'm not sure if you can see this, but I see above the cell that says y_test_scores. It says the training data, and then it says 0, 198, and then it says 1, 2. But that's just a dictionary, so that's just the key of the dictionary, right? That's not the value. And if it was, then those 2s would be around 1 and not 4. So I feel like that's not relevant to what shows up on the graph. So yeah, I'm still just really confused why the leftmost side of the histogram is so close to 0 and so far away from 1.
it sounds like you're trying to understand why the histogram shows values near 0 when the data points are actually close to 1.
Right.
Given the context in your detailed explanation, let's consider a few important factors. Correct binning. Ensure that the bins are set correctly to reflect the values accurately.
Okay.
Potential data transformation. There might be some transformation or scaling applied to the data before plotting.
Yeah.
Training data distribution. Ensure the data you're applying is what you intend to plot.
Yeah.
Let's break down the potential issues step by step. Step by step analysis 1. Check the bin settings. Ensure that the bins and range are appropriately set to capture the high values close to 1.
Okay.
2. Verify data integrity. Make sure y_test_scores is not being transformed or filtered in any way before plotting. If there is any preprocessing, it might affect the histogram. 3. Inspect training data distribution. Check how the training data distribution 0 to 198, 1 to 2 might affect your test before plotting. Although this is just a key value dictionary for classes, ensure this doesn't influence your score applying in any way. Verify the code above and below the plot is a typical way to check the data and plotting. If the data points in y_test_scores are indeed around 1.0, but the histogram is showing values near 0, there might be a mismatch in the data being plotted. Confirm no data scaling or transformation. Check if there's any scaling or transformation applied to y_test_scores before plotting. Possible.
All right. So I don't know if I'm ever going to get an answer for this. We can see the data, which is on X here, is here. So we can see it's 1.0 for most of it. We don't see anything that is like 0.001 as this would reflect. So that's what the book shows too. So it's not just something going wrong on my end. It's very, very confusing why this is happening. So I guess I wanna paste this into ChatGPT just to see what it does with this extra information here. So I'm gonna paste in these two. Oh, and it looks like failed to upload this file, which is new. Oh, okay, now it's working. So something happened where that failed, but now it succeeds. And let's do one more screenshot here and see what the result is of this.
Based on the information in the screenshots, here's what we can discern. Data values. Your y underscore test underscore score array predominantly contains values very close to 1.00 e plus 00, but it also contains two extremely high values, 3.96 e plus 11. These two extreme values are likely affecting the scale of the histogram, causing the other values close to 1 to appear near 0 due to the scale distortion. Histogram plotting. The histogram in the second screenshot shows the leftmost bar near 0, which makes sense if the axis range has been stretched due to the presence of those two outliers. Solution. Adjust the histogram range to get a clearer picture of the majority of your data. You can adjust the range of the histogram to focus on values close to 1 and exclude the extreme outliers.
All right, let's try
Here's how you
that.
can do this. This approach filters out the extreme values to provide a clear histogram for the majority of the data points that are close to 1. Additional step. Plot with log scale. Alternatively, you can plot the histogram with a logarithmic scale to accommodate a wide range of values. Explanation of the observations extreme values. The presence of 3.96 e plus 11 values in your y underscore test underscore score array stretches the x-axis range, making the high density of values close to 1 appear clustered near 0 in a linear scale histogram. Filter
But
range.
the thing
By
is,
focusing the histogram range on the values around 1, you should see a more
no, but I'm not satisfied by this explanation because you can see one is on there. Like look at the x-axis and tell me what it shows. You will see that it shows 0, then it shows 0.5, then it shows 1.0, then it shows 1.5, and so on in these increments. So we're dealing with, in the training data, as you can see, these values that are close to 1, and then these two outlier values that are close to 4, but not quite all the way there. So what you're telling me is that it's distorting the graph because of the values, but why would it do that? Like, I could understand if it was like a logarithmic graph, or like, it was, the x-axis was different from going in 0.5 increments, but the x-axis, I don't see any reason why you can't just put the histogram at 1.0 on the x-axis. This idea that it's distorting it is just a bad idea. Like, I just don't accept this. It's not a good explanation.
Thank you for the detailed explanation. Let's dive deeper into this issue. Key observations data values. Y underscore test underscore score predominantly contains values close to 1, with some extreme values around 4.
Exactly.
X-axis
But
values.
they're not
The x-axis of the
extreme.
histogram ranges from 0 to about 4 in increments of 0.5.
Right. So why isn't
This
it
indicates
right
that the plot is
here?
treating these scores in a linear fashion without any apparent distortions due to scaling. Issues in diagnosis. If the majority of your scores are close to 1 but are appearing close to 0 in the histogram, there might be another underlying issue. Let's explore possible reasons.
But that's
Begin with the
not
range.
it
Bin width might be
either.
too wide, causing all near 1 values to fall into a single bin that is displayed near the start of the x-axis. Seaborn plot function. There could be an issue with how Seaborn's plot function is handling the data. Actionable steps. Let's go step by step to diagnose and address the issue. 1. Print and inspect the data first. Confirm that the data is what we expect. 2. Plot with Matplotlib. Directly use Matplotlib to plot the histogram and explicitly set the bins and range to see if Seaborn's implementation might be causing the issue. 3. Check for plotting function issues plot using another function, like pandas data frame plot, to see if the issue persists. 4. Detailed range focus on the specific range around 1.0 to ensure clarity. Explanation of each step Matplotlib direct plot bypasses any potential Seaborn specific issues. Explicit binning ensures that bins align exactly where we want them. Focus range plot helps in visualizing the dense cluster around 1.0 without interference from other values. Conclusion. By following these steps, we aim to ensure that the histogram accurately reflects the distribution of your data. If the issue persists, it might be worth double checking.
Oh, it doesn't need to listen. Just need to enter.
Thank you for providing the additional images. The issue is now clear with the histograms. Key observations data values. The majority of values are very close to 1.0, but you have a couple of extremely high outlier values around 1.11.
They're not extremely high.
X-axis labeling. The x-axis labels are showing values in range that include 0 to 111, significantly stretching the axis and compressing the distribution of values around 1.0 into a very narrow range.
Oh,
Key insight. The
really?
extreme outlier values are causing the x-axis to stretch dramatically, which compresses the display of values near 1.0.
Maybe I'm
This results in those
misunderstanding
values-
the numbers. Maybe I'm misunderstanding the numbers.
Let's take a closer look at the actual values in the y underscore test underscore score array and the histogram again to understand the discrepancy.
Yeah.
Data inspection first. Let's ensure we understand the data. Print the data. Double check the values in y underscore test underscore scores to ensure they are what we expect. From your previous screenshot, it looks like the values are very close to 1.0. There are two very large values, 3.96 e plus 11. Histogram inspection. Let's create the histogram again, ensuring the bins and range are appropriate. 1. Matplotlib histogram 2. Seaborn histogram focus on specific range since we know the values are close to 1.0. Let's plot focus range. Explanation bins. Using 50 bins between 0 and 1.1 ensures that we capture the distribution near 1.0 in detail. Focus range. VLD. XLIM. 0.99. 1.01. Focuses on values near 1.0, excluding outliers. Extreme outliers. Let's also visualize the extreme values separately. Complete analysis data values. Confirm the actual values in y_test_scores. Histogram with appropriate bins.
But like, why is the x-axis going up by 0.5 increments? Like, I guess I understand that if the outliers are like 3.8 times 10 to the 11, then yeah, those are dramatic, massive outliers versus 1.0, times 10 to the 0. Like, just straight up the number 1. Like, yeah, those are big outliers, and I could understand how that would distort what it looks like on the x-axis. But like the x-axis, oh, I see. So the x-axis does have, I think I get it now. So the x-axis, if you look at the second row of the x-axis, it says 1ELL. So it's the x-axis is actually that number times 10 to the 11. So yeah, the number 1 on the x-axis does not actually mean the number 1. What it actually means is 1 times 10 to the 11. So like if I pull up a calculator and we do 1 times 1 times 10 to the 11. Yeah, so it's basically a logarithmic x-axis, and then I didn't notice that 1E11, so I just got confused thinking that it was increasing in 0.5 increments, but no, it's increasing logarithmically. So now it makes sense because 0 times 10 to the 11 is 0, but 0.5 times 10 to the 11 is an astronomically high number compared to 1. So yeah, the number 1's going to more or less look like a 0 on this graph. Now I get it.
Yes, you correctly identified the issue. The x-axis is displaying numbers in scientific notation, which significantly changes the interpretation. Clarification: the x-axis is showing values like 1 times 10,111 times 10 carats, 11, 1 times 10, 11, 2 times 10,112 times 10 carats, 11, 2 times 10, 11, etc., not simple integers. This makes your values close to 1.0 if you're very small in comparison to these large values, hence why they cluster near 0 on the graph. Proper visualization: to get clear visualization of your data without the distortion from the extreme outliers, we need to adjust the plot to focus on the relative.
Okay, so that's easy. I understand that now. So I need a break. I'll be right back. All right, I'm back. Let's keep going here for a bit. So yeah, I understand it now. We can see there's actually a second row here on the x-axis, and it explains everything. This is scientific notation, so these are values times 10 to the 11. So the value 1 is basically similar in scale from this perspective as the value 0, because the next value on the graph is let's do it. So it's 0.5 times 10 to the 11. So this is the next value of on the graph. So yeah, it's going to be pretty much the same as 0. All right, so that's everything for this notebook. So we've got to move on to the next multivariate notebook. In order to keep things in a limited complexity for our example, and to facilitate visualization, we will extend to 2 variables, mem utilization and CP utilization, in the second notebook for this use case. We have modified our SANS data generation to include now the 2 metrics. So let's switch over to that second notebook, the multivariate notebook. All right, and then let's just do a clear. Well, you know what? As I said at the beginning of the video, yeah, everything's good. So let's not clear things. Let's just go to where we were. So I think. So let's see what the next. So it's sans.generate metric df sans.generate. Which is right at the beginning. So you know what? Let's do it. Let's clear it out and try to get to where the book expects. Everything's already set up. Okay. All right. Okay. Looks good. So now, yeah. So this is where the book expects me to be now with this metric df line. So run that. Like in the previous case, we have already preloaded in the repository a CSV file that contains the data mem underscore and CPU mem underscore and underscore CPU underscore utilization underscore SD-WAN underscore metric dot CSV. Feel free to use this one or to generate new data with SANS. So we're going to generate new data with SANS. That's currently in the works. Either way, we will have a new data frame like the following one. Here are a few things to note as we make progress in our journey to learn data processing. Some of the cells in the table have a NaN. That means not a number. There is no valid value in those cells. Hence, there is no numerical representation. This is a widespread problem you will face as you collect data from the network or other cloud systems. There might be issues in the data or inconsistencies. Your algorithms will not know how to deal with NaN. You first need to resolve, either eliminate those values, if that is an option, or replace it with some other value that makes sense in your context. Maybe a 0, or maybe you need to interpolate or use an average of other rows, etc. The key takeaway here is NaN values are not your friend. It would be best if you got rid of them. All right, so let's see if we got any NaN values, not a number values, in my data that I created. And I made a mistake here. So I'm gonna I think delete these because I don't want to run it from the saved file. And then I'll restart and clear because I loaded it in from the same file by accident. So I have to get rid of that. Okay, so now hopefully we can see the data frame printed out here. There we go. And do we have any NaNs? Not numbers? I don't see any. So we're trying to get so I don't see any so far. So the next line would be metric df equals metric df fill Na0. Oh, so yeah, that was here. So one thing we can do to check if there's NaN is add a cell under and then print out metric df. There. So this will show metric df. You don't need to do a print statement. This is the beauty of the Jupyter notebooks. It will actually show you a visualization of the object. So it won't just show you the words. Okay, so this is why everyone uses Jupyter. So let's see the difference. Let's see it before those NaN are swapped out, and let's see it after. All right, so here's before. So we see we got quite a few NaN numbers. So we got it for CPU utilization. We've got it for mem utilization. Those are the only places, but next we're going to do is prepare the data by replacing those with zeros. And now let's see if that worked by printing it out. And yep, now we've got zeros. But it's about how you handle the data, because it's I think a lot of people can understand there's a big difference between the memory utilization of a device being 0 and there not being a valid reading. Like, what I would rather see is you didn't get a valid reading of it than a 0, because then oh, there's something wrong with these devices. They weren't accessible. TACX is down. They're powered off unexpectedly. That's what I want to know. To just treat it as a zero, I wouldn't really think to do it that way, and I don't think that's a good way to do it. But it's one of the options available. I'm using the most straightforward strategy here to replace them with a zero. This is possible in my scenario because those values are in positions where there is no value. You can see my data of interest is in two different columns, CPU utilization and mem utilization. But SANS created two rows for each device. In one of the rows, it filled, so this makes sense now. It filled the CPU utilization, and in the other one, the mem utilization. So I will end up discarding those values that are not applicable, but I wanted to take this opportunity to illustrate the fact that you will need to find NAN numbers, and you will need to deal with them one way or another. So yeah, now this makes sense. He set up the data simulator in a way so that we go over here and we look at the device name. Each device name is listed twice, and for one listing, if we go up before we swapped out the NAN for 0, the CPU utilization gets an NAN, and then the mem utilization gets a real number, and then for the second entry, vice versa. So that makes sense because that NAN truly is not a, swapping that out for a 0 will, assuming that you add the numbers together, will give you an accurate result for the CPU utilization. So for each entry, you can, now that it's 0, you can just add them together, and now you get the accurate number because it's a 0. If it was not a number, then you couldn't do that, and you wouldn't be able to so easily and gracefully come up with that accurate number, and it would probably be harder to write a generator as well to have to do them both. But yeah, in the real world, if it weren't that way, just swapping it out for a 0 probably isn't something you'd want to just do by default. You'd want to really have good reason for it, as the author has good reason for it here. Now that I replaced the NAN, the table looks like that. And this looks the same as my table. Yep, so duplicate entries for each hostname. I can simply transform my table now in a way that I get the data in the form factor I need. Okay, so transforming it, because I had replaced the NAN by zeros. Yeah, so this is exactly what it's doing, exactly what I came up with. I can do the trick of the sum above and get the result I want by having now one row per device with two separate columns and no interleaved zeros. There we go. So now we can condense it down to one row per device by adding together the CPU utilization and memory utilization values for each device. So each device before had a duplicate entry because it could only do one at a time. The simulator, it could only generate the CPU or the mem. So it did it once for each. For E11, it did an entry with the CPU utilization populated, but the mem as not a number, and vice versa. So the solution to that, to put it all down to one table with no duplicate rows, is now that you've swapped out that not a number with 0, you can add them together, and since it's just a 0, you still get an accurate value. I will drop the timestamp column because I do not need it for this use case. We can visualize the two metrics independently to get a sense of how they look. All right, so advance the bookmark and keep up to pace here. So I've run all the way down to this cell. We can tell that with the numbers here. And with the output, we see there's no output for this cell and no number, so I will run that one. All right, and now we do that summation, I think. Yeah, so So now we're grouping it by, yeah, so here it is, dot sum. So we're summing together. So we're grouping it by device name, dot sum for each of these. Okay. All right, and then the next thing the author does is gets rid of the timestamp because that's not useful. So timestamp is not relevant in this case. We will focus on the memory utilization column and the device name columns. All other columns will be ignored for the moment. Okay, and the author's at CPU utilization in SD-WAN devices. Let's get all the way there. So the author has run this cell and this cell by now. All right. When we look at memory utilization, we can visualize certain devices that appear to be outliers. When we look at CPU utilization in isolation, we also see certain devices that might be outliers. But are those the same or are different ones? What is more interesting is to visualize them together so we get a sense of how device, and there's missing S there, devices, group together based on the metric values. So now we can get CPU and memory utilization. Let's do that. Okay. And then one more here, which will be later on in the book. Okay. By inspecting the scatter plot, we can identify clearly two sets of outliers right here that are indeed different and would have not been identified only looking at one dimension. Let's run again our local outlier factor algorithm, this time with the two metrics in consideration. All right. Oh, so there's so we can see now that the model has detected 6 outliers, and there is a wider variety of LOF, which remember stands for something outlier factor. Shoot, I don't remember what it stands for. That was a while back. Local outlier factor. Okay, so a variety of LOF score values, but it is still clearly differentiable which ones are the outliers. There we go. So we've got a greater variety of stuff here. And then even though they vary so much, we still get outliers from that data, even though the data has so much more variation. Okay, so let's try to get there. So we're going to get to this outlier list cell. So we're training, now we're using local outlier factor rather than what we were using here, which was, I think, z-score. No, I guess I'm confused in that regard, but hopefully all the code will run. There we go. So a lot more different values here. Now it's interesting because these actually don't appear to be scientific notation the way the other ones were. Yeah, and we see there's only one row in the x-axis, so there's actually quite a bit less variation in the magnitude of numbers here. All right. Okay, so we're where the author is now. We can now execute the logic to obtain specifically which ones are the identified outliers. We can visualize the previous scatter plot, but now highlighting which ones the outliers are. So there we go. So the outliers are there. Yeah, so now we're highlighting the outliers. So I guess these are outliers too. Another very popular algorithm for outlier detection is isolation forest. We reviewed in the theory section how it will start building decision trees by trying to find fast data points to find how fast data points get isolated and statistically determine that the outliers are those that soon get isolated across different trees of the forest. We will be using isolation forest class from scikit-learn library. First, we need to create an instance of the class. We will specify two parameters: the number of estimators, which sort of represents the number of trees in the forest, and the degree of contamination that, like in the local outlier factor case, determines the expected percentage of outliers, which will dynamically compute the thresholds in the algorithm. All right, so y underscore pred. All right. And we can print it out to see. So, oh. Sorry, I couldn't find that mute button fast enough. All right, so we got 6 and 194, which will dynamically compute the thresholds in the algorithm. There we go. With the first command, we create the object for the model. With the second command, by calling the fit underscore predict method, we train as well as execute inference for the input data. Finally, we set to 0 those positions in the results vector that the algorithm set as -1. -1 means outlier. The following captures the number of outliers detected by our model. So 6, 124, got the same values. Likewise, we can represent in a scatter plot the results, which are identical to what we obtained using LOF, which remember is local outlier factor. There we go. So let's take a look at that. It should be identical. All right. Just in different colors now. Our third algorithm for outlier detection will be a clustering algorithm, which besides, and okay, I didn't really do a data check until sound check until now. It looks good. So our third algorithm for outlier detection will be a clustering algorithm, which besides clustering our data will give us an indication of what data points do not seem to belong to any cluster. Those will be the outliers. We will use the dbScan algorithm for this purpose. If you remember from the theory, dbScan is based on density and requires a parameter called epsilon, EPS. There is a method that needs to be followed before running dbScan to identify which one is the adequate EPS value. This method is called k-distance. K-distance requires us first to compute the distances between any two data points in our dataset. For that, we need to run the nearest neighbors algorithm. The result of it will be the list of distances between the different points, which we will use to estimate the epsilon parameter. Before running an algorithm that works with distances, particularly Euclidean distances, we need to make sure we standardize the different variables. Otherwise, certain variables may have a stronger weight in the resulting distance, and that would not be adequate. Therefore, we will start by standardizing our data using standard scalar from scikit-learn library. All right, there we go. Now we can compute the nearest neighbors. So we got distances indexes. With this, now we can plot the k-distances graph with which we will be able to get an approximation of the best EPS value. So there we go, plot the graph. And we'll see if the graph I've got looks similar. All right, and it does. As we observe the graph, the point of highest slope in the graph has an EPS value around 0.4. Intuitively, this means the point at which data points in our dataset become more abruptly separated, which may be the right boundary for cluster separation. We can then run dbScan algorithm. We are also using the scikit library for this. So here we go, dbScan equals that. Looks good. The parameter min_samples is also domain specific and defines how many samples should be in a cluster to consider it a cluster. We have set it to 10. In other use cases, the right value might be different. We can explore the detailed values returned by the model in terms of the cluster labels provided. This is how it looks like. So there we go, dbScan_labels. All right, so here's the dbScan, and this is how it looks like. We can observe there are various clusters detected labeled as 0, 1, 2. The observations labeled as -1 correspond to those identified as outliers. If we plot the data again in a scatter plot view, we will clearly visualize the outliers dbScan has detected. All right. Scatter. Okay, so we get this. So it's just showing how we can get, we can do this in various, using various methods. The results are consistent with what the previous algorithms have indicated. All right, so takeaways. Some key, and I'll run the rest of the, I don't know why it's, yeah, I don't know why this code is, I don't know what this is for, but anyway, we're on the takeaways. So some key learnings from this use case and the approaches showcased that I would like you to take. Like in the previous case, there is always a subjective angle to the definition of what an outlier is or is not. Therefore, domain expertise is always required for proper interpretation and fine-tuning of the algorithms. And that's a great word for ChatGPT. So to learn more about this, tell me what kind of domain expertise would be necessary. Yeah, domain expertise.
Understand and address issues like one you encountered, you would benefit from expertise in several domains.
Yeah.
Here's a breakdown of the relevant areas and why they are important. 1. Data science and analytics key areas. Data visualization. Understanding how to create and interpret visual representations of data, such as histograms.
Yeah, so that's a great thing to prompt chat. So like act as an expert in this domain expertise and give me 5 important things to consider.
Sure. Yeah. As an expert in data science, statistics, and data visualization, here are 5 important things to consider when dealing with data analysis and visualization, particularly in the context of the issues we discussed. 1. Handling outliers consideration. Identify outliers. Use statistical methods, e.g., z-scores, IQR, to identify outliers in your data. Impact analysis. Understand how outliers can distort. Yeah.
So look at how that word or that phrase, domain expertise, can be used in ChatGPT. Really valuable phrase to use there. An outlier may be used on one metric, but if we look at other metrics, it may not be. When there are multiple metrics, we should consider evaluating multivariate outlier detection. High memory utilization may be perfectly acceptable if we consider other variables in play. There are multiple techniques available for outlier detection. We have simply explored some of the simplest ones, but at the same time quite effective. Like in the anomaly detection, no one-size-fits-all. Data must be cleaned before running algorithms. NaN, not a number of values addressed, data scaling issues resolved. Anomaly detection. Outlier detection and clustering all share strong commonalities. All are unsupervised and try to find structures within the data. structure of what is normal and what not, or how the entities group together as a means to also identify what is not normal. Further work. As a suggestion, if you are motivated, it would be interesting to try other algorithms. Also, explore adding more variables to evaluate a higher dimensionality. As part of that, when you add more variables, it could also happen that some of those variables are not that useful, so you could try dimensionality reduction techniques to optimize which ones are the optimal variables to use. You could try with other entities in SANS, for example, metrics on interfaces to find potential anomalies or clusters. All right, so finished up use case 2, use case 3. What different types of SD-WAN devices do I have deployed? So we'll dive into that in the next video, but for now I got through everything. I got all the notebook to run, everything. And we actually learned a really good prompting word for ChatGPT. We learned domain expertise. That's a great prompting word to use. So that's it for this video. Thanks for watching and see you in the next one.